starting chapter 3 and dealing with functions. Our first section, 3.1, is functions and function notation. So first of all, we're going to identify a few vocabulary terms. The first thing being a relation, which is just a set of ordered pairs. So here's a set of ordered pairs. That makes it a relation. The set of all the first components is called the domain. We've used that word a lot. Also, you might see it referred to as an input value or the independent variable. So in this case, the domain is all the first components of the ordered pairs. So we get 1, 2, 3, and 4. So that makes up the domain of my relation. The set of all the second components is called the range, also called the output value or the dependent variable. So for our range, it is made up of 2, 4, 6, and 8. So just a few vocabulary items. So how do we tell if it's a function? Well, a relation is considered a function if each domain value is paired with a unique range value. So in other words, the domain values can't repeat. So if we look at our previous example and notice the domain values, I have a 1, a 2, a 3, a 4. They do not repeat, which makes this a function. So it's a relation, but now we know it's also a function. So taking it a step further, we have something called a one-to-one function. And once we've identified it's a function, it may be a one-to-one function. And what we mean by that, each range value or output value corresponds to exactly one domain value or input value, which means that the range values can't repeat. So to be a function, the domain values cannot repeat. To be a one-to-one function, neither can the range values repeat. So let's take a look at a familiar function, f of x equals x squared. And notice here are some of the domain values, because we know that for the values of x, I could have picked anything, which means that the domain is all real numbers. But just looking at a few of the ordered pairs that satisfy this function, notice that we see that we have, first of all, none of the x values are repeating, but when x equals negative 2, the y value is 4. When x equals 2, and I guess I could have called this f of x instead of y, we also get a 4. So the range values repeat, which means that even though it's a function, it's not one-to-one. Okay? An easy way to check if a relation is a function is by looking at the graph and applying the vertical line test. Can you draw a vertical line anywhere on the graph and pass through 2 or more points at the same time? If so, then the relation is not a function. So for example, f of x equals x squared. Notice my vertical dashed line, and it only passes through 1 point on the graph at a time. If I were to move this along here, it would still only pass through 1 point. Notice my graph, my x equals y squared, my relation, and I can see here just visually that it passes through 2 points right here. And there's other places where it would pass through 2 points. So this is not a function. However, this is a function. So the vertical line test gives us a really quick look to see whether or not a relation is a function. So we're going to extend this idea to verify from a graph whether or not a function is one-to-one. And we can do what we're going to call the horizontal line test. So back to our function, f of x equals x squared. And let me change colors on this. I'll just use yellow. So if we did a horizontal, now we know it's a function because it passes the vertical line test. Oh, yellow is not a very good choice. But if we do a horizontal line test, we see that it passes through 2 points here. So it's a function, but not one-to-one. Okay, So looking over here at our g of x equals x cubed, you can see that it passes the vertical line test, which means it's a function. And it also, if you take a look here, would pass the horizontal line test. I just picked a spot, but you could have drawn that horizontal line anywhere, and you'll see that it only passes through one point at a time. So this is one-to-one. Now, if it's not a function, it doesn't make sense to talk about whether or not it's one-to-one. So you'd want to identify that it was a function, and then you can talk about whether or not it's a one-to-one function. Another way that we can represent a relation is in table form. So here's a table of values, and I want to determine if the relation represented in the table represents y as a function of x. So what are we looking for? Well, the domain values are all my values of x, so I'm looking to see whether or not any of my domain values repeat. So since the domain values do not repeat, it is a function. Now, what about a one-to-one function? So we know that it's a function, the domain values don't repeat, so now we want to know if it's one-to-one. We'll look at the y values or the range values. Not one-to-one because we have range values that repeat. Okay? Function notation, and I've actually already been using it, and we used it last year. Function notation is useful to describe a relationship between two variables. For example, we can describe the relationship between the height of a rocket as a function of time since liftoff. So if you were going to do something like that, using a t for time, and h of t tells us that height is a function of time. So often it makes sense to use variables that represent the situation and that it makes actual sense. So h for height, t for time. Or perhaps the profit earned from selling a number of items. You might use p of n, where profit is a function of items sold. So it just gives us a little bit more information about the variables than just using an x and a y. So just like we often use x and y as generic variables, we often use x and f of x as generic variables in function notation. So you'll see that used quite frequently. So here's an example. Given that f of x equals 2x squared plus 3x minus 1, find each of the following. So we need to evaluate f of negative 1. Well, remember that x is our input value, so this is telling me to input a negative 1 into my function any place where I see an x. So I'm going to evaluate that. Now I recommend that you always put parentheses around the value that you're dropping into that variable so that you don't make a mistake, especially right here. We're squaring a negative 1. We get 1 when we do that, so we're going to have 2 plus negative 3 minus 1. So we get negative 2. So we would say f of negative 1 equals negative 2. F of 2, we're going to substitute in a 2. So we get 4 times 2 is 8, plus 6 minus 1, or 13. So remember what that means. The domain value is 2, so this input, if I input a 2, the corresponding output would be a 13. So for this one here, now remember what this means, x plus h becomes the input. So wherever I see an x in my equation or in my function, I'm going to replace that x with an x plus h. So I get 2 times the quantity, I'm going to have x plus h quantity squared, plus 3 times x plus h minus 1. Now this one requires a little bit more effort, a little bit more algebra. You're going to have to multiply this out. You can FOIL it or put it in a box. When you do that, you'll get x squared plus 2xh plus h squared. Distribute the 3. And now I'm going to distribute this 2. and see if I have any like terms, and I don't, so that actually would be done. And I know that looks really kind of crazy complicated for an answer, but those of you going on to calculus, you'll do this as part of a process when you are learning about derivatives, and you have to do this algebra, so learn it now. Part D is a little different. If you take a look at what it's saying here, it's actually asking you to solve f of x equals -1. Now remember, x is my input, f of x is my output. So this is saying for what value of x is f of x equal to -1. So that's a little different. I'm not just going to substitute a -1 in for x. This is the f of x value. So I'm going to take 2x squared plus 3x minus 1 and set that equal to -1. Well, remember, this is a quadratic equation that I'm trying to solve. So we always get that equal to 0. So I want to zero this side out. So I'm going to add 1 to both sides. Oops, don't want to do that. So I'm going to add 1 to both sides. So we get 2x squared plus 3x equals 0. Now I'm going to factor out an x. Using the zero product property, either x equals 0 or 2x plus 3 equals 0, which would give me x equals -3/2. So I would have two answers when I solve that. We can also talk about function values from a graph. So suppose you're given a graph and x is my independent variable, f of x is my dependent variable, and I'm asked to evaluate f of -2. So this is saying if I have an input value of -2, what's my output value? So I go to my graph and I find -2, and then I have to just kind of check my graph and see what the output value is. And the output value would be 2, because that's the height of my function. The next part says to evaluate f of 4. So that means the input value is 4. So I go along here, I find the 4, and I'm looking for this value right here. Now I could make sure I could use the slope of this line and double check, but it appears to be 1.5 or 1.5. And then this last one, notice this is different. It says solve for f of x equals 0. So now this 0, this is the output value. This is saying for what value of x is the output value, or that we can consider that the height of our function, equal to 0. So this time I'm looking for the height of 0, which is right here, and I want to know what x value makes that true. And so you can see that x equals 5. So that's how you do dealing with function values from a graph. And our last one here, here's an example. Let d of t be the number of ducks in a lake t years after 2002. Explain the meaning of each statement. So just trying to understand what this sentence would mean. So the t, remember, represents the number of years, and the d of t represents the number of ducks. So this 5 here is representing 5 years after 2002. So that would be the year 2007. So we can say in the year 2007, and then we want to know how many ducks there were. Well, there were 30. There were 30 ducks in the lake. And this one, if 10 represents the years since 2002, so we would say in the year 2012, there were 40 ducks in the lake. Okay, so that is it for section 3.1. Those are all the high points. So you will be able to get started on your assignment.